The plan for today, we're going to finish section 15.5. That'll finish up chapter 15. But before we get into that, let's start with homework questions or questions in general. Does anybody have anything they want to talk about? Okay. Well, if you change your minds. Oh, okay. Yes. Go ahead. Okay, I'll wait. I'm a waiter. 151 or 152. Okay. Oh, we haven't done this yet, so this part shouldn't have been assigned. So you're good. My apologies. So we're going to talk about that today, and it'll be super clear as what to do. And okay, well, that's easy then, right? That's my mistake for we're going to do those problems eventually. I didn't read them closely enough when I wrote them down, so we'll get that squared away today. Oh. Is that cool that I just tabled to Victoria? Yeah. Okay.
So does that mean our review in the next class after this and then the test?
That would be what we're looking at. Okay. So recall in the previous class, we talked about our compound interest formula. Right, everybody kind of remembers this. And we looked at the effect of K, right? We looked at when K was 1 annually, 2 semi-annually, 4 quarterly, 12 monthly, 52 weekly, and 365, so daily, right? What we want to look at now, maybe we'll write that stuff. What if we have interest compounded continuously? What value of K does that imply? What's that? Yeah, infinite. So we can't exactly plug infinity in for K and get a number to come out, right? So let's play with this formula a little bit and see what we need to do here. So in order to kind of make this work, what we're going to do is we're going to rewrite the exponent. So instead of writing the exponent as n times k, I'm going to write it as 100k over r times nr over 100. Now you might look at that and go, why? What in the world did you just do? Notice if you multiply those two fractions together, everything reduces down and you just get nk. So I haven't really done anything differently. I've just written this in an odd way. And I'll show you why I wanted to write it in this odd way in the next step. And it's because I'm going to make a substitution. So I'm going to say that x is going to equal r over 100k. Oops, I'm sorry. 100K over R. Okay, so I'll make that substitution then. Now, if X is 100K over R, what is R over 100K got to be? 1 over X. And then I have 100K over R in the numerator, so that's an X. And remember, if I have exponents that are being multiplied, that's the same thing of like an exponent of an exponent. So I'm going to write it that way. So far, so good? Does anybody recognize this thing? We talked about it this chapter. Let me go back and find it here for us. Where are we? Right here. That was part of our definition for E, where E is the limit as x goes to infinity of 1 plus 1 over x to the x. Everybody kind of remember that now that I've refreshed your memory to it? It was before spring break, so you're perfectly excused for forgetting that. I would have been pretty surprised if you did remember. And since I have k going to infinity, then I know certainly that 100k over r would be going to infinity, right? And that would imply then that x goes to infinity. So what that tells me then is I can just take all that stuff in blue and replace it with an E. And this is now our third interest formula. This one specifically for interest compounded continuously. And again, I'm not going to redefine FV, PV, N, and R. Those are all the same quantities as last time. We're okay just writing the letters if it's all the same things. Okay. Let's run through a quickie example. So here we have that Jack invests $800 into a savings account with a 5% annual interest rate compounded continuously. How long will it take for Jack to have $500 in interest? So first thing I need to do is identify which of the three interest formulas I need to use. So which two words in here am I most interested in determining which formula I should be using? Yes, very good. So that phrasing, when I see that, tells me the formula that I need to use. And I know it seems kind of redundant that I'm making like this big of a point, but a lot of the difficulties here just come from like making sure we're comfortable with the vocabulary and what things mean, right? Because you have three formulas to choose from. How do you know which one to choose? It should tell you in the problem. And how does it tell you it? Maybe not directly like use this formula, but like the wording should tell us. Okay. In this problem, what are we being asked to solve for? How long? So that means we're looking for the number of years, which is n. So we're going to have to fill in everything else. All right. So where does the 800 go? That's the PV. Very good. And where's the 5% go? That goes into R. And then what's going to go into FV then? We have actually not 500. 1,300. Why did you get 1,300? Yeah, it's the present value plus the interest, right? Which will give you the future value. So you just have to be a little bit careful there. Again, the wording in the problem makes a big difference. That it's $500 in interest, not $500 for the account. That'd be a pretty crummy investment, right? If you put $800 in and you get $500 out. Oh, man. All right, so to solve for n, what would I do first? Except not subtract, divide. There you go. And I'm going to just reduce all this stuff just to make our lives a little bit easier. Actually, I'm going to leave that parenthesis there, I think. So 1,300 divided by 800, just 13 over 8. That's pretty easy to see. And then 5 over 100 reduces down to just 1 over 20. So I reduce the exponent also. Not critical that you do that, but you know, if it's easy to do, I'm just going to do it because it's less writing for me. Next step would be to so we're going to need a logarithm to cancel the exponent base. The logarithm that we need in this case is log base e, also known as the natural log. And the symbol for the natural log is ln. Cool there. And the last step would be to multiply each side by 20. Yes, sir. And now it's calculator time. So I get about 9.71 years. Everybody okay there? Again, the solving techniques have been the same that we've been using for like the last 2 lessons. So like nothing surprising there, just a new formula that we need to set up the problem with, right? But it's a pretty easy formula to use. So that's good. All right. New example, unrelated to the previous one. So let's say you find an account that has a 6.5 annual interest rate compounded monthly. My question then is, what's the equivalent interest rate for an account that's compounded annually? So let's look at kind of what we would need to do there. So we're going to be kind of setting up 2 different equations. One for monthly, one for annually. So I'm just going to organize my work a little bit. Now we have 3 interest formulas. Which interest formula do I want to be using here? Yeah, just the regular compound interest one, since neither of them are being compounded continuously. All right. Now we haven't been given like a ton of information here, so we're going to have to be a little bit clever with how we interpret things. So where is the 6.5 going to go? R for which situation? Monthly. So also for the monthly we have the K. Everybody so far so good? All right, and then it says, what would the equivalent interest rate for or an account that's compounded annually? What information can we pull from that sentence? Yeah, so that gives us the K is 1 there, right? Okay. Well, let's just, I guess we can simplify over here a little bit. I can get to there, right? That's pretty obvious. And what I'm going to do in the monthly side is I'm, again, going to use that exponent of an exponent property to rearrange things a little bit. And now if I compare these two equations, what parts are identical? All of that stuff, right? So what is that going to mean? Those parts have to be equal then. If they're going to be equivalent, if they're going to be earning the equivalent interest, those two parts have to be equal. You guys buy that? Since they're basically saying they have to do the same thing. So to get the R by itself, what do I have to do? Subtract the 1, and then, well, negative 100, right? Oh, sorry. I don't know why I wrote down a negative sign there. It shouldn't have been a negative sign. It's supposed to be a positive sign. So just multiply by 100. And so now it's calculator time. So 100 times 1 plus 6.5 divided by 1200 to the 12th, and then minus 1. And I get about 6.7%. Is everybody okay with this idea? So this is a really important idea because it allows us to compare different account situations, right? Like if I have an account earning 5.6% interest compounded weekly and another option that's like 5.55% compounded, continuously, which one should I pick? Well, the idea would be we do this to each of them, convert them into annual interest rates, and then pick the one that's bigger. Everybody okay with that idea? So that's going to lead us to our next financial definition. This is the annual percentage yield, or APY. This is what, Victoria, you were asking about. This is the interest rate for an account if it were compounded annually. So we're doing the exact same process that we did before, but I'm going to formulaize it, like turn it into a formula. So if we look before, we have 100 times 1 plus, and that was R over 100K, to the K minus 1. So there's my APY formula, where the APY is just the interest rate if things were compounded, for the equivalent annually compounded interest rate. So again, as I mentioned, the most most useful way why this is useful is that it makes comparing two different situations fairly obvious which one is the better situation. So let's do an example of doing that. It says, which savings account is the better investment? One that pays 7.8 compounded quarterly, or one that pays 7.65 compounded weekly? So when we say it like this, it's like, oh, I don't know, which one is better? Well, what we're going to do is we're going to convert both of these into APYs and pick the one with the bigger APY. It makes the comparison really easy. Is that okay? And we'll set up both of them, and then we'll go to the calculator. Everybody's cool with how I plug things in, right? Just R and K are the only two inputs, so it's pretty easy formula. Oops. One plus. And I'm going to use the fraction command here so that I can just go back and edit my work for the second one. I don't have to retype everything all the way. So the first one is 8.03% for the first account. The second one, I need to go back and I need to change that 4 to a 52. And I need to change that 4 to a 52. And then need to change that 7.8 to a 7.65. So the other is 7.94%. So which is the better investment? The first one or the second one? The first one, because the APY is bigger. So far, so good, guys? Again, no big deal. Understanding what you're doing there, though, is helpful, and that it's like all you're doing is really converting this to an annual interest, to the equivalent annual interest rate. And once you have them on the same compounding period like that, it's trivial comparing them. It just, the bigger one is better. Yeah, well, okay. Easy enough.
So that's getting mostly like problems like these like formulas we've learned.
Well, the test is, I haven't finished writing it yet, but there's 5 sections. There's a lot of stuff. But we'll talk about the test format some more next week on the review day and what to expect. I'll have a much better answer for you in terms of that when I'm finished doing it. You know what I mean? I hate to tell you like what it's gonna be like, and then when I'm not done with it, kind of. You know what I mean?
Yeah.
Okay. The next thing that I want to define is a financial concept called an annuity, and this is an account where, well, maybe we'll say into which a sequence of payments are made and in particular that sequence of payments, or there's a special type of annuity, I should say, called an ordinary annuity, which is in particular the one that we're going to be talking about and the one that's the most interesting to us. So an ordinary annuity is an annuity where all the payments occur at the same time and for the same amount. So when we talk about an annuity, what does this sound like? What kind of normal financial things does an annuity sound like? What kind of financial thing would you do that you make regular payments? Okay, so like on a loan, like a mortgage or a car title or whatever, car loan. What else? Where the payment's always the same size. So loan payments for sure, that's a great one. The other one, the reason you're coming and not being able to come up with it is it's something that doesn't even come into your mind, is I would say retirement savings. Typically people save like the same percentage of their check every month for their retirement, right? So that's another situation where like you're doing a regular investment into a 401k or an IRA or whatever financial product you're using, you know, to house your retirement savings. So those are kind of the 2 situations that we're going to talk about, either like a retirement savings account or a loan. So our annuity formula is FV equals R times 1 plus I to the capital N minus 1 all over I. So here there's some new letters, right? Cap R, little I, and cap N we haven't seen before. This is the cap R is our ordinary payment. So that's the, you know, what your monthly payment is on your loan or how much you're investing each month in your like savings account or whatever. Little I is just R over make sure I have it. Yep, 100K. So nothing really to define there, since it's I is just defined in terms of R and K that we already know what those are. And then cap N is just going to be N times K. All right. And again, we know what N and K are, or little n and little k. So no issues there. All right. So let's run through an example. At the end of each quarter, Sarah makes a $500 payment into an annuity account. If her investments earn 7.88% annual interest, compounded quarterly, what will the value of Sarah's annuity be in 20 years? I heard the words annuity in there, so I knew that we should be using this equation. Okay. So what are we solving for here? In the future, right? So we're looking for the future value. All right. Let's start filling some things in then. What is the value for R? 500, that's the ordinary payment. So the payment amount that you make every so often. And I'm going to write it, I'm not going to fill in a number for I or cap N. I'm just going to write off to the side the equation for little I, since it's, so little I was 7.88, the interest rate, over 100 times K. What's the K in this case? So 4. And then the cap N is going to be little n times K. Everybody feel okay with that? So I'll just go to my calculator. And here it is, I'm going to abuse the heck out of the fraction command. If you haven't been using the fraction command, boy, it makes typing this stuff in like a whole heap easier, because you can just more or less type it like it looks like on your sheet of paper, and you don't have to go like parentheses crazy on things. But this stuff was a pain in the tuchus to type this stuff in prior to the calculators having this updated operating system. So like even like, I don't know, probably 5 or 6 years ago, most people's calculator didn't have the new math type operating system where you could write a fraction in, and you had to like really be super careful with your parentheses because you needed a lot of them. But here you can just kind of type it in the way it looks like on your paper, and it's makes it way easier. So what do we get? We got $95,483.39. So this is this annuity formula that I gave you initially was like an investment annuity, right? if we have a annuity as a loan, things work a little bit differently. Since what's happening on a loan? Right, you owe some sum of money, so you have like some big negative balance, and each time you make a payment, that negative balance gets a little bit closer to zero, right? So the formula, if we have a loan situation, is a little bit different because instead of like your value growing, it's going to be decreasing. And if you take out a loan, what are you often the most interested in from a practical standpoint? What the payment's going to be, right? What do I owe every month? Can I actually afford to buy this thing that I'm interested in? Like, can I buy this house and afford the payments on it? Or can I buy this car and afford to make the payments on it? That's the piece as a customer we're going to be most interested in here. So note here that we use the term present value. Probably in the case of a loan, it's easier to think about it as the principal value. That's how much you borrow, right? So like when I take a loan out, now I have like essentially I have an account with a negative balance. So if I take a loan out for $10,000, I basically have a balance of negative $10,000 in my account. Everybody's okay with that idea? And the I and the N are the same as the other ones. All right, I got two more examples for you guys, and we're going to be Audi 5000. Sound good? Yeah. Since we're talking about buying cars and stuff. All right. So Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and the annual interest rate is 2.9%? So I heard loan in here, right? So I'm going to be using the loan version of our annuity formula. And what are we being asked to solve for in this problem? So we're looking for R. What is the payment? Everybody feel good so far? All right. So let's start filling things in. What do we fill in for PV? It is not 18,500. What is it? It's not 2,000. It's not 2,100. Other way around, but yes. So if you think about what happens when you buy a car, you walk in, you pay for some of it up front, that's the down payment, and then you borrow the rest. So our PV is going to be the price minus the down payment. So that's 16,500. Okay. And just like before, I'm going to write down the values for I and N here off to the side because I'm not going to fill all that stuff into the formula because it gets pretty gross looking pretty quick, right? What's the the I is R over 100K. So what's the I in this case? Or the R in this case? 2.9. That's good. And what's the K in this case? $12, because the payments are happening monthly. And my N is, well, the K is 12. What's the, how many years are we talking about? 4. Okay. So what I'm going to do then to solve for R is I'm just going to take that 16,500 and divide it by that whole big mama jam over there. Okay, so that's how I'm going to type this into my calculator. So I'm going to do fraction command. I'll do my 16,500. And in the denominator, I'm going to do parenthesis fraction command again. And I have 1 minus 1 plus. And then where the I is, I'm going to do the fraction command again. I'll do 2.9 over 100 times 12. Close my parenthesis there. Go to the exponent and do negative 4 times 12. Move to the denominator in the denominator and do another fraction command there. So that's, again, 2.9 over 100 times 12. And then go back and close my big parenthesis there. And I should be good. So I get $364.49. So that should lead you to the interesting question of how much did we actually pay for the car and how much interest did we actually end up paying? So let's do the total cost for the car. How do we calculate that? Okay, so we paid $2,000 for the down payment. So then we have our payment. And how often do we make that payment? Once a month for 4 years. Everybody cool with that? That's correct though, Landon. Good job. Good job remembering the down payment. That's the piece most people forget. So we end up spending $19,495.41. $18,500 would be a good price for that particular vehicle you just quoted.
That's what I calculated.
Okay, so how much did we end up spending in interest? We'll just take the total cost and subtract the price of the vehicle. Right? Because everything else off other than the price of the vehicle was part of the was the interest. So we spent $995.41. Any questions? No?
It's pretty simple. It's just like a lot.
Yeah, by and large, this last section, was doing the same things we've been doing all chapter. We're just have some new formulas that we're using, and it's mostly just calculated. In fact, the solving things that we have to do here are often quite easy solving things to do, right? The equations are pretty easy to deal with in comparison to some of the things we saw in the last section. Understanding the financial concepts is sometimes easy for us and sometimes maybe a little bit more challenging, but for the most part, you know, it's kind of common sense. If you've had like a job and had some bills and like, you know, like gone car shopping before or any, you know, these things that are kind of helpful, like real life experiences to have to give you some context here. And some of us has done those, some of those things, and some of us haven't. So like how easy that these last questions appear, you know, differs just based on life experience. You know what I mean?
Yeah.
Okay. We'll stop here. You guys can spend the next, we got 30